Hello, my name is Ross Higgins. I am the course director of the engineering course in UL, and I would like to thank you for joining me as I present an overview of LM116 Engineering Common Entry. I'm also joined today by Ronan Grimes from Mechanical Engineering, Con Sheehan from Design and Manufacture Engineering, David Newport from Biomedical Engineering, Vanessa Egan from Mechanical Engineering, and John Mernan from Civil Engineering. We're also delighted to have co-presenting Rena Cole, who is the Assistant Dean of Academic Affairs. So these are my co-presenters, and they will be able to answer some questions that you might have via the chat function. So before I get into talking about what engineering is and what the engineering course in UL is all about, I'd like to describe some of the things that make UL stand out. So one of our former presidents coined the phrase the UL edge, and he used that to describe the advantage that UL graduates have over the graduates of other programs. And it's all down to the employability prospects of our graduates, which over the last 10 years has been well above the national average. That is due to the industry links that the university has with a whole range of companies, but in no small part also due to the success of the co-op office, whereby students are placed in companies for a period of up to 8 months. The university also has the largest international exchange program. Engineers are increasingly working with more and more international collaborators. So it's important for engineers to just get used to dealing with the cultures and the backgrounds of international people. You in UL, especially in engineering, you will be working or you will be studying with international students, and you might have the opportunity to go abroad for your co-op placement as well. It is a beautiful campus, and it was awarded the best student campus in 2019. It is probably the reason I work here in UL. It has a whole range of facilities and services, and I'll describe those to you more later. There are a whole range of supports from maths and science learning centres to the first 7 weeks program. So the first 7 weeks program recognises that early adjustment leads to subsequent success in your academic career. And finally, UL is, or Limerick is, Ireland's most affordable city for rental accommodation. So during this presentation, I'd like you to self-reflect and ask yourselves what interests you, and if it's the problem solving of potential engineering that might interest you, well, this course might be for you. So engineering is the creative application of maths and science to design and build things. And the scale of things might vary from the smallest components in electrical devices to large scale, maybe infrastructural projects. And as a civil engineer myself, I love the big scale. Usually I might ask the audience for their opinions of what the largest infrastructural or engineering projects in the world have been. So if you want, you can enter into the chat some ideas for what you think the largest engineering projects ever built have been, and we might just discuss what those are in the end. So while you're self-reflecting, I might just describe how it was for me. I recall vividly the building of our family home in 1990, and I recall just being fascinated by the build, the construction of it, brick by brick, to ultimately dwarf me. And as I learned about skyscrapers, And again, as a 9 or 10-year-old, I remember then being fascinated by the county hall in Cork. So while I play this next video, I'd like you to ask yourselves, what interests you? So engineers design and build buildings and bridges of all sorts. We build and design infrastructure for transport, like rail services, airports, ports of all sorts. We design and build tunnels. On campus, we have the Irish World Academy for Music and Dance, and you can be sure that that was acoustically designed. If we're in a lecture theatre, you'd imagine how important lighting design would be. And of course, the most important part of all buildings is foundations, and understanding how those are supported is very important as well. You might be on a project where you're looking at blast analysis. Looking at means of escape from buildings is very important. And of course, looking at citywide infrastructure from public transport systems to a whole range of other services is something that engineers must do as well. There's lots of scope in engineering for creativity, and here is the Millennium Bridge, that's the Water Cube, and Bird's Nest Stadium in Beijing. You might remember those from the Beijing Olympics. Fluid dynamics is important, not just for modeling river flow, but certainly for biomedical engineers as well, looking at head traumas. And we are problem solvers. Addressing the UN's Sustainability Development Goals means that sustainability needs to be at the forefront of all engineering design, meaning reducing our carbon footprints and generating our electricity from renewable sources. And you can see the wide spread of applications there that engineers are involved with. So I hope that video has just prompted some ideas as to what things that you might be interested in. So just to describe the course, it is the entry to study biomedical engineering, civil engineering, mechanical engineering, and design and manufacture engineering. So you do this engineering common entry program for 1 year. And of course, after your first year, you branch off into one of those 4 disciplines. And after 4 years, you can exit with a Bachelor of Engineering qualification. There is, of course, a 5th year option in civil engineering and in mechanical engineering, where graduates can graduate with a master's degree. The minimum points requirement this year was 476. And of course, there is, like in all universities, to study engineering, you need a H4 in maths. There are, of course, other requirements such as an 06 or a H7 in another science subject. And I think there are 10 of those science subjects. If you don't get the H4 maths, there is a special math exam, and that's held in UL each August. So if you pass that special math exam, and again, it's at the same standard as the higher level maths. If you pass that and you meet the other minimum requirements, you are entitled to join the engineering program. So in your first year, there are 2 semesters. There is an autumn semester which starts from September to Christmas, and then a spring semester, which starts from, let's say, mid-January to, let's say, the end of April or so. During the middle of your spring semester, you will be asked to select your preferences for your programs for year 2, 3, and 4. So you'll have to log on to the system and select your first preference, your second preference, your third preference, and your fourth preference. So it could be, for example, first preference biomedical engineering, second preference civil engineering, and so on. And then at the end of the summer, we will look at your preferences. We will also look at your summer exam performances, and we will allocate students to each of those programs. Now, if a program is oversubscribed, i.e. if there are more first preferences than spaces available on each of those programs, well, we look at the UL exam results and we distribute students based on those results. So there's no guarantee that you will get your first preference. However, the vast majority of you will get your first preference. Last year, 94% of students got their first preference. So in the first year, you will study a range of foundational science, maths, engineering, computing type subjects, and then you will kind of just build on those in the subsequent years. So in the second year onwards, when you're in your particular disciplines, you'll do some more foundational subjects where you'll do more maths and science, and you'll do some specialization. When you finish your summer exams in year 2, you will begin your 8-month work placement. So typically that'll start from, I don't know, like start of May until Christmas. The exception is if you're studying civil engineering, you'll do that for the second half, right through until the summer of third year. And of course, even though there's like overlap between the various engineering disciplines, you will be, as you're progressing, you'll be further specializing. And of course, whether you're going to exit after 4 years or exit after 5 years, there's going to be a significant research project at the end. So if you're studying, let's say, biomedical engineering, you might have your final year project in your 4th year. If, for example, you're studying civil engineering and you opt to do the 5th year, well then you would not do a final year project, but you would do a significant research project, which would be a master's thesis in your 5th year. And the image on the right describes how students, even from 1st year onwards, they complete the full design process or the full engineering process of designing and building or operating. And as you progress, the projects just kind of grow in complexity as your level of specialization increases. So the next part of my module just goes through some of the information regarding the 4 particular modules. So I'm going to start with biomedical engineering. And biomedical engineering is probably one of the newest disciplines of engineering. It's kind of branched off mechanical engineering, whereby initially the purposes would have been to insert inert materials into the body, such as hip replacements, but it has now progressed into looking at cells and tissue and working with cells and tissue, manipulating them and actually reinserting those materials back into the body. So you're looking at kind of just biomaterials, if you like. And certainly there's definitely a trend within biomedical engineering towards cellular engineering. So again, working with cells and tissue to just solve problems. Biomedical engineering covers 4 aspects, so medicine, pharma, diagnostics, and devices. In medicine, this means working with doctors to design practical solutions to the problems that they face. In pharma, biomedical engineers develop drugs and treatments that help people. In diagnostics, engineers design machines that can diagnose and analyze and treat people. And biomedical engineers design medical devices that, such as stents, that are directly inserted into the body and directly assist people. So from year 2 onwards, you will study discipline-specific subjects where you learn about the engineering of cells and tissues. In 3rd and 4th year, you will learn about fluid mechanics, engineering biomechanics, medical device design, and biomaterials. You'll also build computational models of biomedical systems, such as what's shown here, which is a model of a diseased aneurysm. And here's a computerized tomography scan of a patient with an aortic aneurysm. Finally, with biomedical engineering, you can see the spread of employers that employ biomedical engineering graduates, and some of them are very, very close. In fact, they're literally down the road in Castletroy. Moving on to mechanical engineering. So mechanical engineering is it's a subject that's concerned with the design and manufacture of parts and systems that make up a range of like machinery and equipment, from can openers to jet engines. And graduates of mechanical engineering are prepared for work in many sectors, from energy to automation to automotive, manufacturing, materials and processing, and chemical processing. Mechanical engineers are involved with the generation, distribution, and use of energy. They're involved with the design, planning, and development of machines and equipment, and with the design of automotive and aeronautical machines and components. Basically anything with a moving part in it. So we can see the 3 images on the right. We have some Formula 1 cars, we have wind turbines, and we have a gas turbine on the bottom right. So a mechanical engineer might, for example, if he or she is looking at the suspension of a car, might look at the dimensioning the suspension and just ensuring that the stresses within the components of the suspension, that they resist the forces that are applied to it, forces from the bumps of the road or accelerations and decelerations. And of course, there's just movement all the time going on with suspensions, and engineers must ensure that they are efficiently designed. Of course, not over designed, because they would be just too heavy and too expensive. Mechanical engineers would look to optimize the wind turbine blades so that they would maximize the energy that's generated from the wind, and therefore maximize the amount of electricity that is generated. And of course, they would obviously need to design the blades such that they can withstand the forces exerted on them. And of course, you could imagine that forces would be cyclical forces. So a fatigue failure would be a likely failure mode. And a gas turbine then might be found on the underside of an aircraft wing or in a power plant. And like with that of the wind turbine blades, mechanical engineers must design the blades to optimally transfer power. This becomes quite challenging, as you have you have to deal with high temperatures from the combustion with such a process. From year 2 onwards, you will study subjects like heat transfer, energy management, engineering materials, fuels and energy conversion, control engineering, applied mechanics, and mechanical design. You will complete projects in several modules throughout the program, culminating with your final year project or your master's thesis. And they involve a significant piece of research, and some examples include the design of energy efficient houses, the exhaust system design, stress analysis of a composite material at the fiber length scale, and the optimization of turbines for tidal power. The images there on the right describe some of the other types of projects that students might have been involved in. So the image there with the colors is a finite element analysis output showing the modeling of a stress near a crack. So it's contoured such that the blue to red colors describe an increasing stress, with red indicative of high stresses. And then on the right, we have the wave turbine. Students have previously completed projects where they design wave turbines for generating energy from the waves. And here we can see a very, very comprehensive spread of companies that employ mechanical engineering graduates. And of course, lots of them are very, very local, and some of them are household names such as Bord Gáis and ESB. Next is civil engineering. So civil engineering, building on the original definition of engineering. So civil engineering then would be the creative application of math and science to design and construct civil projects, such as like just the design of the built environment. And this word cloud here describes some of the things that are involved in it, ranging from roads to bridges to houses, and it's a real important profession. Much of engineering involves very practical things, but there's often scope for creativity. This is art. This is a pedestrian bridge in England, and it's beautiful. And it also serves as a crossing for thousands of pedestrians and cyclists every single day. And my favorite, the Millau Viaduct. This is the tallest bridge structure in the world. Each of those towers is actually taller than the Eiffel Tower. Civil engineers can make dreams come true. There are several twisty skyscrapers like this. This one is from Moscow, and this would be an instance where an engineer would have to work very, very closely with the architect to make this a reality. And maybe closer to home, maybe some of you might recognize this or not. Well, this is the main structure behind an iconic building in UL, the Analog Devices building. And that building has a particular feature. It has a very, very significant cantilever on the western side. That's it in its kind of finished day view. And I'm glad to say that it was actually a civil engineering graduate that completed the design for that. So even though it was tricky design, there's absolutely no fear of it. And of course, civil engineering really involves designing and building for the public, designing for the community, hence the word civil. So you can imagine how rewarding it would be to be involved in projects where you're actually improving the quality of lives for like thousands of people every single day. So for these kinds of infrastructure projects, such as kind of rail projects, or what we have on the right, which is the Limerick Tunnel. You can imagine how these pieces of infrastructure, they might save commuters 10 or 20 minutes every single day. When that's multiplied by all of the users every single day of the year, multiplied by a whole multiplied by the number of years of the lifespan of that project, it does become this significant benefit to a community. Similarly to this is just a crossroads, but it's actually a grade intersection. It's a grade intersected project, or a grade separated project, I should say, where we actually have two motorways crossing, and I think it's the only case in Ireland where two motorways are crossing perpendicularly to each other. So we have the Tuam to Gort motorway crossing under the Galway to Dublin motorway. And in this case, you have just like a significant piece of infrastructure that allows for the continuous flow of the traffic for each of the 16 possible turning movements at that junction. So there are 4 arms, there are 4 possible turning movements from each arm, including a U-turn, and all of those are facilitated in a continuous fashion. So the engineering behind it is really significant. And very, very close to home is the Ord na Crusha hydroelectric power station. This was built actually almost 100 years ago, and was designed by Thomas McLaughlin, who is an Irish engineer, and whose name is on one of the UL main building's towers. So there are 3 main themes within the civil engineering program. There's structure and infrastructure, there's energy, and there is environment. And those themes are touched a number of times throughout the program. The images that I've shown you here of the roads and bridges and buildings, they are indicative of the types of projects that students on the civil engineering program will be doing, but also indicative of the types of projects that graduates of the civil engineering program would be doing. So next to design and manufacture engineering. So design and manufacture engineering covers a range of topics that are directly relevant to solving real-world problems. The program encourages students to design useful working products, seeing them developed from possibility and design through practicalities of use to real use and eventual recycling after their life's end. Students build on their skills and aptitude for design and analytical work and cover a range of subjects, including fundamentals of design and production, computer-aided design, automation, materials, quality, capacity planning, and simulation. Students also become very proficient with SolidWorks and use the CDIO teaching and learning approach, which stands for conceive, design, implement, and operate. And there's an emphasis also on team projects. By the end of the course, you'll be in a position to manage the life cycle of new products, from design through production and on to the end of life recycling. And this image here describes the full design and manufacture process from the specification of materials through to the end user experience. The testing for the main project of a first year elective module comprises a public event. It's the UL car race. So the module Introduction to Design and Manufacture introduces students to engineering drawing, to basic manufacturing processes, and to workshop equipment. And the flagship project is the UL car race, where students design, build, and compete. So in teams, they must design and build a device to carry a bottle of water up a short slope. And here we see some of the innovation within the program. The bottom left image is a support mold for 3D printing. You can 3D print the mold on the right, put it into housing on the left, and then put it into conventional injection mold. So injection molding is great for producing thousands of products, but it can be quite expensive, and 3D printing can be quite slow. So this technique has been, I guess, innovated here within the program of design and manufacture engineering. It's called rapid tooling, and it uses the kind of benefits of both systems. Finally, on design and manufacture engineering, we can see the list of employers that would typically employ design and manufacture graduates. Just a word on the co-op placement. It is a fantastic opportunity for students to build on their experience from the university courses, but also to just develop their communication, creativity, and collaboration skills. This is a student from civil engineering that I visited a few years ago. Placements are organized by the co-op office, and students can be placed locally or globally. And of course, lots of students end with job offers in their back pockets when they finish. There are a number of supports, including the first 7 weeks, which I've described, whereby specific guidance and supports are given to students over their first 7 weeks. There's an advisor system whereby every single student is allocated, typically a lecturer who might be their first stop for any issue, academic or otherwise. And there are maths, science, and information technology and communications learning centers whereby you can drop in or you can make appointments and get supports as required. And finally, one of the best things about UL are its facilities. In the arena is one of only 4 50-meter pools in the whole country, and there's a second pool. There's a gym, and there is a very, very big sports hall there in the arena as well. We have lots of outdoor facilities. We have an adventure center in Calloo, and we have a world-class boathouse in the corner of the campus as well. We have the university concert hall for lots of shows and events. Maybe some of you have been there already. And we have scores and scores of clubs and societies for students to join during their time here. That's the end of my presentation. I hope you got a bit of an overview of the program. I try to give you an overview of the 4 options. And now